Hello, Mr. Betts here. I want to look at kind of a shortcut that we can use for integration by parts. It's particularly going to be useful for problems where we have to use integration by parts multiple times to get to an answer. So I want to go through a particular problem here where we're going to use integration by parts, but we're going to have to use it multiple times. And then I'm going to look how we can reorganize that work to do this problem a lot faster. So first thing I'm going to do here is I'm going to choose my u and my dv. Remember, I want to choose u so that when I take the derivative, it gets simpler. My dv, so when I take the antiderivative, it doesn't really get more complicated. So I'm going to choose the e to the 2x for my dv, and that leaves u is x squared. So both of those are going to work for what I was looking for there. Du is going to be 2x, and v is going to be 1 half e to the 2x. That 1 half, because of the chain rule, you can confirm that by taking the derivative. When we multiply by the 2 because of the chain rule, the 1 half goes away. So making our substitutions in the integration by parts formula, this is going to equal u times v. So it's going to be 1 half x squared e to the 2x minus the antiderivative of v du. And for simplification purposes, the 2 and the 1 half cancel each other out, and that's just going to be an x. So notice that we still have a product here, which means that we need to do integration by parts again. So I'm going to choose u equals x, and dv equals e to the 2x. So du equals dx, and v equals 1 half e to the 2x. That should have been dx on there. And so this integration by parts here is strictly for this expression right here. So rewriting, first term is just going to stay the same. Then we're going to have minus. So this negative here, I want to make sure I distribute that to both terms in the formula for integration by parts. So we have u times v, so 1 half times x times e to the 2x, minus, but remember the negative is going to distribute, so really plus the antiderivative of v du. The 1 half I'm going to put out front. So we have e to the 2x dx. So now I'm in a position where I can evaluate this antiderivative without integration by parts. So everything else just comes down. And then the antiderivative of e to the 2x is going to be 1 half e to the 2x. So we're going to get a 1/4 e to the 2x. And when we do that final antiderivative, don't forget that plus c. So there's our work. Like I said, I do want to go through the same problem, but show you a way that we can organize our work a little bit more efficiently. In order to do that, I want to look at the work that we did here. And I'm going to make one little change. Instead of canceling the 2 and the 1 half here, I'm just going to leave those here. And that's going to give us a 1/4 and a 2 here. And I want you to notice that we multiplied this times this, and then we multiplied this times this, and then we subtract the integral of this times this. And evaluating that integral or that antiderivative was pretty straightforward. It was just a matter of evaluating the antiderivative there. So if we reorganize our work, and instead of choosing our u and dv over and over again, I'm going to choose my u and I'm going to choose my dv, and I'm going to just repeatedly take derivatives and repeatedly take antiderivatives as long as I need to. So I'm going to make the same choices I did before, but I'm going to put them in columns because I'm going to have For my first step, a du, and then for my next step, a derivative of that, just like I essentially took the derivative of the x squared here and then take the derivative of it again here. Now, I'm actually going to take that a step further. So I'm going to take the derivative, take the derivative. I'm going to take that one step further, and I'm going to take the derivative one more time. So the idea with tabular integration is once we choose our u and our dv, is we're going to take derivatives of u until we get to 0. Now, in the dv column, we're going to take antiderivatives, and we want an antiderivative for every one of our derivatives. So we're going to have 1/2 e to the 2x, and we're going to have 1/4 e to the 2x, and then we're going to have 1/8 e to the 2x. Now, the last thing that we're going to do, if you notice here, so I do want to point out that that the 1/2 e to the 2x and the 1/4 e to the 2x pop up in our work here. The last thing that we're going to do is we're going to multiply along those same diagonals that we did here. So we're going to multiply there, we're going to multiply there, and notice that the second term here was subtracted because of that minus in the integration by parts formula. So multiplying these diagonals here. So the first one's going to keep the same sign, so I'm going to put a plus there. The next one's going to be negative. The next one's going to keep the same sign, so the negative distributes with the negative and becomes a positive again. If we were to have another one, we'd be multiplying that by a negative because of the negative in the integration by parts formula. And we're just going to multiply those out, and that's going to give us our answer. So we have x squared times 1/2 e to the 2x is going to be 1/2 x squared e to the 2x. So that was these two multiplied together. Then minus, now I'm doing these two right here. So it's going to be the 2 times the 1/4 is 1/2 x times e to the 2x. And then I'm doing these right here. The 2 times 1/8 is going to be 1/4. So plus 1/4 e to the 2x, and then plus c. And that's our answer. So notice that we got the exact same answer, but the amount of work that we did is significantly less. Okay, so one more time, here's the process. We're going to choose our u and our dv just like we normally would for integration by parts. However, we're going to write it a little bit differently. So we chose our x squared, we chose our e to the 2x, and then once we choose those, we're going to take derivatives of u until we get to 0, and then we're going to take antiderivatives of dv to match. Once we do that, we're going to multiply along diagonals and alternate multiplying by a positive one and a negative one along every other diagonal. Look for a couple examples in the example videos on more about tabular integration.